Welcome. We're going to start again with duality today. We're going to finish up finish up Tuesday's lecture, and then we're going to move on to the Kkt conditions. And we have kind of a lot of stuff to cover, so I'm going to try to make sure we cover all of it because we don't want to get too behind. We have some exciting stuff coming up in future weeks. But please do stop me if you have questions, because I'll try to be going a little more quickly today. So just to review what we learned last time, we talked about the Lagrangian, which is, we're given this general minimization problem. It looks like this. We have an objective function f. We have constrained functions hi and equality constrained functions lj, and these need not be convex. So for now, we're going to say they're just functions, but of course, we're interested in that case because we can say a lot more in that case than in the general case. But regardless of convexity, we can define this quantity called Lagrangian, where we just define a variable ui for each one of the inequality constraints and vj for each one of the equality constraints. And Lagrangian looks like this. It's f plus the sum of ui hi and the sum of vj lj. And we're going to constrain these variables u to be positive in each coordinate. Okay, so that was just a review of last time. One of the properties of the Lagrangian is that it's always smaller than or equal to f if x is feasible. So if I take any u and v and u is positive in each coordinate and x is a feasible point for this primal problem, which means it satisfies these inequalities, then it's always smaller than or equal to f. So it lower bounds f everywhere over the feasible set. And that comes just from the fact that this is 0 in the feasible set and this is non-positive, so the whole thing is smaller than or equal to f of x. Okay, so if we minimize f over the feasible set, that gives us f star, our optimal primal value. That's bigger than or equal to minimizing the Lagrangian over the feasible set, which in turn is bigger than or equal to minimizing the Lagrangian over all of Rn, because if I extend the domain of minimization, it can only get smaller. And this function here, which is only a function of u and v because we've minimized out x, this is what we call the dual function. Okay, so we denote it by g, and it's a function of u and v. So for any u and v such that u is positive in each coordinate, we know that this function provides us with the lower bound on the primal optimal value f star, right? Just from this argument right here. And to get the best lower bound possible, we actually maximize this lower bound over all possible u and v, for which u is positive in each coordinate. Okay, so that was maybe a minute-long construction of the dual problem that we learned last time. So a very quick summary of the dual problem. Just from our steps, by construction, we have this property called weak duality, which means that if g star is the optimal dual value and f star was the optimal primal value, then we know that f star is bigger than or equal to g star. That was by construction. If you go back over those steps, it'll be clear why that's true. Just because the Lagrangian always lower bounds the function, and that's where it comes from. So this always holds even if the primal problem is not convex. And another key property, which is the property that we finished on last time, which is again a very simple argument to prove this, but it's maybe a bit of a surprising result, is that the dual problem is always convex. Even if the primal problem is not convex, the dual problem is a convex optimization problem. So here there's a little bit of an abuse of notation. This is just how we talk about these things usually. A convex problem, right, is of the form minimize a convex function over a convex set. That's what we call convex problems, convex optimization problems. Or we can also say maximize a concave function. This one would have to be concave over a convex set. So why are they both convex problems? Well, right, this problem is really the same as minus min minus f tilde of x over x and c. Right, so if f tilde was concave, then this is convex. So some people are a little bit confused about that last time. So convex problems, we either minimize a convex function or we maximize a concave function. They're really half a dozen, or whatever the expression is. They're the same thing. Somebody can fill that in for me. We can edit the video. So yeah, so the dual function is concave, and we're maximizing it, so it's a convex optimization problem. Okay? And that comes from a very simple argument. We take a look at its definition. It's the minimum over all x of f of x plus the sum of ui hi and the sum of vj lj. I did the same trick here with it as minus the maximum of minus all of this stuff. Right? And as a function of u and v, this is a convex function. In fact, it's affine in u and v. So I take the maximum of convex functions, even though it's the supremum because there's an infinitely many things I'm taking the maximum over. That was one of our operations that preserved convexity. This thing is still convex. Right? So the minus of this max is concave, which means that g is concave. So we're maximizing a concave function, which we know cannot have local maxima. So that's something that we like about the dual problem. In general, if the primal problem isn't convex, it's usually pretty hard to derive the dual in closed form. So even though we know that it is a convex optimization problem, it's usually kind of hard to get at it explicitly. So just to finish up with last time's lecture, I wanted to give you guys an example of a non-convex problem and its dual. So here's this this function I defined, f of x. It's equal to, it's univariate x to the fourth minus 50x squared plus 100x. It's non-convex. Here's a picture of it right here. Right, you can tell immediately from the picture that it's not convex. Right, it has this bump here. And I want to minimize this function subject to the constraint that x is bigger than or equal to minus 4.5. So the reason why I chose this example is that if you think about how you derive the dual in this case, and I'm going to not cover it because we're short on time, but you follow the steps for deriving the dual. We add basically u times x up here into the objective, and we want to minimize that over all x. Well, that gives us, if we differentiate it, since it's smooth, a cubic equation, right? And the roots of a cubic equation, we actually have a closed form expression for that. So it's not as simple as the roots of a quadratic equation. It's kind of messy, but there is a closed form for that. So the hope in constructing this example is that I could actually give you a closed form for the dual for a non-convex problem. That's why I chose this function in the first place. So the dual, when you derive it, if you go through the steps, it's extremely messy, and it's very non-obvious that it's concave. So there's factors of its variable, which is u, and the numerator and the denominator to many different powers. And if you look at it, and that was a function you're given, it would be hard to say whether that was concave or not. It doesn't come from any kind of simple operations that preserve concavity. But we know it's concave, right? Because of what we just proved, which is kind of interesting. And in this case, I just plotted it rather than giving the expression, and this is what it looks like. Okay, so here's the primal criterion. Here's the constraint, and if we want to minimize f subject to being to the right of this line, it's this red line here. And the dual function provides a lower bound on that primal optimal value, which is this red line. And you can see we don't get what's called strong duality here. There's actually a duality gap. So G star is actually strictly less than F star. Questions about that? Okay, so that brings us to strong duality. Remember we said we always have that F star is bigger than or equal to G star. But in some problems, like this quadratic problem that we talked about last time, and in the max flow min cut example, we had strong duality. We actually had that the F star was equal to G star exactly. So there's a very general condition under which that's true, and it's a very nice result. It's called Slater's condition. And it tells us that if the primal problem is convex, that means that f and the inequality constrained functions are convex, and all these equality constrained functions L are affine. Remember, that's how we define a convex problem. Then this result tells us that if that's true, and there's at least one strictly feasible x, meaning that it makes all of the inequality constraints satisfied with strict inequality, and the equality constraint satisfied, then strong duality holds. Okay, so as long as it's a convex problem, and we can find an x in the domain such that these are all strict and the equality constraints are satisfied, then we get strong duality. So that's very general, right? So for a lot of the problems that we're looking at now, we're going to see that we get strong duality. this can actually be further refined. You can actually say that even if you have inequality constraints, but those inequality constraints are on affine functions, you actually only need strict inequalities for those non-affine inequality constraints. Okay, so that's an even weaker form of Slater's condition. So just to go back to where we started last lecture, we talked about linear programs and LP duality, and we had this question, when do we get strong duality? And there was kind of a mix of people. Most people thought we always got strong duality. Some people thought we didn't. So now that we've studied duality, we have the answer to that. You can go back and check by just calculating it on a piece of paper that the dual of the dual LP is the primal LP. So if I start with the primal LP, I derive the dual, and I take the dual of that, you can check that you get back to the primal, which is probably reassuring that you're not kind of going in some loop that doesn't close. Then if we look at the more refined versions of Slater's condition, it tells us that strong duality holds for an LP if it's feasible, right? Because for an LP, every constraint is linear. So what does Slater's condition say? It says that if we look at this weaker version, as long as there's an x that satisfies the constraints, we get strong duality. Right, so I take, let's just say primal LP. We know that if it's feasible, then we get strong duality. If I go and I apply the same result to the dual, right, then I also have the result that if it's feasible, then we get strong duality. Right, so even if the primal was infeasible, but the dual was feasible, we still get strong duality. So that means that the only time that can happen that we don't get strong duality for a particular LP is if both the primal and the dual problems are infeasible. Okay, so if there's no x that satisfies the primal constraints and there's no u and v that satisfy the dual constraints, then we don't get strong duality. Which means that the primal optimum is plus infinity and the dual optimum is minus infinity. Okay, so in that case, most likely we wouldn't want to be solving those problems in the first place. So we can rephrase that by saying that we pretty much always have strong duality for LPs. Question?
Do they have to be convex problems?
So for LPs?
Yeah, primal LP.
Yeah, so for LPs it's always convex. Yeah. Right, we have just a linear objective with linear constraints. And if you look at Slater's condition, which was this general condition, we do have the precursor here that the primal problem is convex. So which is why, for example, in this problem, right, clearly there is a point that satisfies this inequality strictly. I can just take x equal to minus 4, right? That satisfies that inequality. But the primal is not convex, so we're not guaranteed strong duality here by Slater's condition. Another question?
I guess it's kind of hard for me to envision a situation where the primal is feasible, or one of them is feasible and the other one is not. Could you sort of expand upon that and maybe give a condition where this happens?
Yeah, so the question was, if we have an LP, when would it be the case that the primal is feasible, but say or the primal is infeasible, but say the dual is feasible, something like that. So I think is it this lecture? We can maybe go back to the start of this lecture and talk about a case where that would occur. So, okay, if we take a look at these problems, right, so let's suppose here that p was negative. P was minus 1. Okay, so in this case, the primal is feasible, right, but the dual is not feasible. Because they have to have non-negative a and b that sum to something negative. So in this case, you can see that the primal optimum is actually minus infinity, because I can just keep taking x bigger and bigger and I'll drive it down to minus infinity, but the dual is not feasible. By convention, we always make the maximum of something infeasible minus infinity, we still get strong duality. Good question. Any other questions? Another question.
When will the dual actually help in solving the problem?
Yeah, it's a very good question. So the question was, basically, what's the dual going to buy us in terms of actually solving the problem? At the end of today's lecture, we're going to start talking about that. And the next 2 lectures are going to be almost exclusively about that. So especially the second lecture of next week is going to be all about the uses of duality. So in a lot of cases, the short answer is it's going to help a lot, and we're going to be able to learn when you might want to go to the dual because it is helpful. Uh-huh. Another very good question. So the question was, if I have a general problem, I take the dual of a dual, when is that the primal? And we're going to talk about that next Tuesday. So again, the short answer is that it's going to happen mostly all the time. Okay, everyone's predicting what we're going to learn. So I'm going to have to skip, unfortunately, for the sake of time, this example on matrix games. I had this game where Jeff and I were competing. Jeff was going to win, probably. But actually, we're going to tie. That was the point of the example. But I encourage you to go through this, and maybe, who's doing the recitation next week of the TAs? Is it Kevin? Well, I don't see Kevin, but maybe Kevin can cover this in detail in the recitation. It's basically an example in which we have 2 LPs and we get strong duality. But what that means in terms of a game theoretic consequence is kind of surprising. Okay, so today we'll talk about the Kkt conditions. So I just did this review, so I'm going to skip this. Lagrangian Lagrange dual function, and might as well just repeat this because it's all in one slide. Dual problems always convex. Primal and dual optimal values always satisfy weak duality. And Slater's condition, which is that we have strict inequalities. There's some x that give the strict inequalities and equalities for all the equality constraints, implies strong duality in the case of convex problems. So just a preview of what we're going to learn in the next 2 lectures, but also because I wanted to say a little bit more about duality before leaving it. We're going to talk about something called the duality gap. Oops. Guess I'm out of paper. I have another one, which is good. I planned ahead. We went through an entire binder of paper. So, okay, so this quantity right here, f of x minus GUV, if x is primal feasible and u and v are dual feasible, this is called the duality gap. Okay, so what do we know about it? Right, we know that this is called the duality gap between x and uv. We know it's always non-negative, right, by construction. And if it's 0, then we know that actually x is a primal solution and uv are dual solutions, right? Because we know that, for example, f of x star is bigger than or equal to GUV for all dual feasible u and v. And conversely, we know that for all primal feasible x, f of x is bigger than or equal to g of u star v star. So if we ever happen to make those equal, then we actually have primal solutions and dual solutions. Okay, so this is true for any dual feasible uv and for any primal feasible x. Okay, another way of writing this, which is maybe another helpful way to see it, is that by construction, we have that this is true. Okay, so if I take f and I subtract off the optimal value, it's going to be smaller than or equal to the duality gap at x and uv. So this is important for a bunch of reasons. One of the reasons that it's important from an algorithmic point of view, right? If I'm solving both the primal and the dual problem simultaneously, and I happen to be at a point where I have some iterate x and some iterate uv, say it's suppose it's an iterative algorithm, then if I look at this duality gap, then from what this statement tells me, I'm guaranteeing myself an upper bound for how far away from the primal optimum solution in terms of the function value. right? So if I stop this, and this happens to be epsilon, then I know that I'm at most epsilon away from the primal optimal value in terms of my function value. And conversely, the same thing's true with the dual. I know that G minus G star is, again, at most the duality gap. Okay, so a lot of iterative methods. I think we're going to cover interior point methods coming up. I don't know if you plan to cover primal dual interior point methods, but it sounds like we will at least talk about them. We might take a step in the primal, a step in the dual, evaluate the duality gap, and if it's too big, we'll keep going. So we talked about stopping criteria for gradient descent, and those descent methods, they're all pretty vague. If we actually can evaluate the duality gap, that's a very kind of concrete stopping rule, right? Just stop when the duality gap's small. It guarantees that we're close to the optimum.
So this is an answer to, I forget who asked the question, what's the dual good for, right? This is actually really important, because it doesn't actually matter what your algorithm is that gives you the primal feasible point and the dual feasible point. People have come up with, for a specific problem, crazy algorithms for somehow getting yourself a primal feasible point and a dual feasible point. And once you get them, you can look at them and you can say, I'm no more than this far away from the optimum because the duality gap is no more than this.
So we'll be talking a lot more about dual uses coming up. Here's one other connection I want to make, and we'll be talking about connections to other types of duality or other uses of the ideas of duality. We talked about dual norms a bit through this class. And in particular, we made this definition, or we made this observation earlier on, that if you have a norm, okay, and common examples are these LP norms, where we take the absolute value of each entry. I'm missing a P there, I'm sorry. So write the LP norm of X is, I take the pth power of each entry, and I add them up, and I take the 1 over pth power of that whole thing. That's an example of a norm, like, for example, p equals 1 is this L1 norm we've been talking about quite a bit.
You don't want the p to be, you want the sum to go to n or k or
Sorry,
whatever
thank you.
vector is.
Confusing. So if X is in Rn, right, that's what we'd say. Another example of this norm was this matrix norm that we used. I'm actually changing the notation slightly. You're going to see why in a second. Just putting this subscript nuke. So the nuclear norm, remember, is the sum of the singular values of a matrix. That's also a norm. So we talked about the dual norm, which I'm going to denote by, if you give me this norm, its dual is going to be denoted by just a star at the bottom. We define this as, I look at all z that are within the unit ball of my original norm. I take the maximal inner product of z with my point x, and that gives me the dual norm of x. That was something we'd observed or even defined earlier in class. This gives us immediately this inequality, right? That in absolute value, z transpose x is smaller than or equal to the primal norm of z times the dual norm of x, right? Because if I have z transpose x, I can always think of the point z over its primal norm as having primal norm less than or equal to 1, so that's at least one feasible point in this max. Right, so the maximum is going to be bigger than or equal to, x, which is equal to the max of, say, all u transpose x, for which u is smaller than or equal to 1. That's bigger than or equal to, just if I take z in particular, so which gives me z transpose x over z, or in other words, z transpose x is going to be smaller than or equal to z times x. And the same argument could be applied in the reciprocal direction to give me the negative sign. So this gives us this Cauchy-Schwarz inequality, very useful for a lot of reasons with these dual norms. And if we go back to our examples in particular, I'm not going to derive these, but you can go through them on your own, or you can look in our textbook. They have the derivation of some of these in there. The dual of the LP norm, for example, is the LQ norm, where 1 over p plus 1 over q is 1. Okay, so another very useful fact. And the dual of the nuclear norm is the spectral norm, which is the largest singular value. All very useful facts. So why do we call this the dual norm, how does this relate to dual problems? We're going to learn all this coming up, and we're going to see that knowing these facts and thinking of the dual norm can help a lot in deriving dual problems for a lot of important statistical machine learning problems. Another fact is that the dual of the dual norm is the dual norm. So we saw this with LPs, the same fact. If you take the dual of the dual, so x double star, it's just the original norm. Okay, so all those connections are going to be coming up in future lectures. So today we'll talk about the Kkt conditions, give some examples. We'll kind of go back to a pretty common topic in statistics and machine learning, which is constrained versus Lagrange form of problems. And I'm going to finish with the results on the uniqueness of solutions when we have a one-norm penalty, to give you a somewhat in-depth example of the use of the Kkt conditions, less of a toy example. So here's our setup again. We have this general minimization problem, minimizing f subject to some inequality and equality constraints. And I'm just going to tell you what they are. The Karush-Kuhn-Tucker conditions, which we abbreviate as the Kkt conditions often, are a set of 4 conditions, and they're as follows. The first is that 0 is a subgradient of the Lagrangian. So Lagrangian here is f of x plus the sum of ui hi and the sum of vj, that should be a j, vj lj, with respect to x. So if I take the Lagrangian, I consider it as a function of x, I take a subgradient, then 0 should be a subgradient. Basically saying that x minimizes the Lagrangian over all x. That's called stationarity. The second condition is that ui times hi of x is equal to 0. So what does that mean? That means that, for example, if hi was strictly smaller than 0, then ui has to be equal to 0. But if hi was equal to 0, ui can float around. I have to have primal feasibility, so x has to satisfy the primal constraints, and this is called dual feasibility, right? We talked about dual problems. If you think about this as the dual variable, then it has to be non-negative for every coordinate. So those are the conditions. I haven't connected those to anything important yet, but I've just stated them. So we're going to work through this together instead of stating the results and then working through them. So let's think about necessity. So for example, if I had x star and u star and v star, and they were primal and dual optimal, okay, so x star, u star, v star, and they're optimal for their respective problems. Let's also suppose that the duality gap is 0. And that happens, for example, when we have strong duality. Okay? So then through a bunch of simple arguments, we're just going to basically prove that those Kkt conditions are necessary for optimality. Okay, so by assumption I have that the duality gap is 0, right? But by definition, the dual function is just the minimum of the Lagrangian over all x, and I'm evaluating at u star v star, so I can write that like this. Right, so that minimum is, in particular, it's going to be smaller than or equal to this if I evaluated x star, because it's the minimum. So if I evaluate at any particular point, this gets bigger, at most less than or equal to. Right, and because x star was primal feasible, and we know that Lagrangian was smaller than or equal to our function everywhere, it's particularly smaller than or equal to f at x star. So what have we said? In other words, we said that all of these inequalities are equalities. Okay, so in particular, both of these are equalities, and those are going to imply some interesting things. So if we look at this one, I've said that these two are equal. That implies that x star minimizes the Lagrangian over all possible x. Right, so what's a necessary and sufficient condition for that? Well, it's exactly what we wrote down. It's that at x star, I'm going to have a 0 subgradient. If I'm taking a subgradient with respect to x of all these functions. Important to remember. Okay, so that's exactly the stationarity condition. So we've just proved stationarity. Okay, now if I go back to this one right here, I've actually said that these two are equal, right? I might as well just write them as equalities so nobody's confused. That implies, well, first of all, this is 0 for feasible points, and this is non-negative. So I've actually just said that this is equal to 0. Right, but since each of these terms is less than or equal to 0, in particular that means that each ui star times h of I at x star is equal to 0 for all I, because they can't have opposite signs. Okay, and that's complementary slackness. So this one was stationarity, and this one was complementary slackness. Okay, now obviously the primal and dual feasibility conditions hold, right? We said that we're going to assume they're solutions, so they're obviously feasible. So what we've shown to summarize is that if we have primal and dual solutions and they have zero duality gap, then the Kkt conditions must hold. Okay, so that means that they're necessary for optimality. So it's important to note, maybe just to keep this in the back of your mind, there's nothing here a priori about convexity. So if we happen to have a non-convex problem for which strong duality holds, and there are some, certainly, then the Kkt conditions are still necessary. Let's go the other direction now. Yeah?
In your problem definition, is HI of x less than equal to 0?
Hi of x is less than or equal to 0. Yeah.
So when in that, you could show each term is less than equal to 0.
Sorry, yeah. I have a typo here in the slide. Although it doesn't matter.
Yeah.
As long as they don't have the same sign, then it's going to imply that they're all 0. But thanks for pointing that out. Okay, so let's think about the other direction. So let's suppose we had points that satisfy the Kkt conditions, and we're going to try to figure out when would be the case, when can we say they're actually optimal. Okay, so let's start with G. I'm using the star notation perhaps as slightly an abuse of notation because we don't know they're optimal yet, although we're going to prove they're optimal shortly. But we just know they satisfy the Kkt conditions. So if they satisfy the Kkt conditions, then for example, I can write this as an equality, right? Because the Lagrangian is equal to f plus ui hi plus bj lj, all stars here. But one of the conditions is that right, each of these is 0, and this is 0 by definition of feasibility, so I get an equality there. So I can immediately say that if we satisfy the Kkt conditions. And I just expanded this here as the same thing. Right? And because each of these is 0, I get exactly f of x star. Okay? Sorry, I'm trying to think why I wrote convexity here. I've temporarily stumped myself as to why we need convexity, but I'm sure it's important. Otherwise, I wouldn't have written it down.
Sufficient to use zero stationarity.
Yeah, I don't actually need to say that it's convex. Okay, well, there's a subtlety here, but usually when we write the stationarity condition, we write it as gradients instead of subgradients. And the subgradients are only gradients when it's convex. So the standard way to state it is that the primal problem is convex, so that you can write the stationarity condition as actually, instead of subgradients, I just take gradients here. Okay, but those are only the same thing when the problem is convex. If we happen to satisfy these conditions, then actually it implies optimality whether or not it's convex, but we're just going to use convexity so that whenever we have a differentiable problem, we don't have to worry about the subgradient not being equal to the gradient. Okay, so for these steps, this word's not necessary, but it's actually helpful to have this whenever we talk about differentiable problems. Okay, so what we've just shown through like one step basically is that the duality gap is 0 if the Kkt conditions are satisfied. So what does that mean? That means in particular, like we said previously, that they're both primal and dual optimal. This pair. X star is primal optimal, and U star V star is dual optimal. So the converse of our statement is that we've shown that for a convex problem, if this pair satisfies the Kkt conditions, then they're primal and dual solutions. Okay, so let's just summarize, put it together. If I have a convex problem that satisfies strong duality, so for example, when would that hold? If I had a convex problem with Slater's condition, then both those conditions hold. Or I guess convex is assumed in Slater's condition. Then what we've shown is that X and this pair UV are primal and dual solutions if and only if the Kkt conditions are satisfied. So it's both a necessary and sufficient condition for convex problems in which we have strong duality. Okay, so it's a really nice summary, a nice characterization of optimality.
Even if not a convex problem.
I'd like us to think about convex problems all the time, because if I have a non-differentiable, if I have a differentiable non-convex function, then the subgradient is only the gradient if it's convex. So when we talk about subgradients, it's something that always lower bounds the function, right? And if the gradient lower bounds the function, then it's convex. So in general, if you had something that was differentiable but non-convex, you could fool yourself by writing down gradients here, and that actually would not be the stationarity condition. So I didn't want to cause that amount of confusion, so we're just going to think about convex problems. If you have a non-convex problem, then you have to find a subgradient of your function, which may or may not be the gradient. So it's a more difficult task. So sorry for that confusion. Okay, so just think about this, this last box here. That's what we've achieved. Any more questions?
So how did you prove that given if X star, U star, V star satisfy Kkt conditions? We don't know if they're optimal yet.
Yeah.
So then how in these three steps did you prove
Right, so I said, let me just move this G up here and you'll see it. So I started off by saying that now I think I've also confused myself. Let me think for a second. Yes, thank you. Thank you very much. Good point. Right, so G is equal to the minimum let's just write this out so we all can be on the same page. G is equal to the minimum over all x of f of x plus ui star thank you and Vj star Ljx. Okay, and in particular,
Because of stationarity.
thank you.
So,
Goodness. Because of stationarity, right, this is minimized at x star. That's what the stationarity condition tells us. Exactly. So you can see that all these simple statements can be confusing, but that's kind of part of the beauty of Kkt conditions and duality. There's not very complicated arguments. We arrive with powerful statements, but they come from very simple arguments. So because of stationarity, right, which told us that x star was a subgradient of this function, we know that this is true. Okay, but then by complementary slackness, that's 0, and that's always 0, so we get exactly x star. So we've just proved the duality gap is 0. So stationarity actually always implies minimum. It's again because I'm using subgradients. But you're right, if I had gradients there, it would mean it's an extreme point. But I'm using subgradients, so it always means that it's minimized. Another question? So the question was, if I have this condition, I also need convexity to say that it's minimized. But I'm saying that if you go and look back at how we define subgradients, a necessary and sufficient condition for any function to be minimized, convex or not, is that 0 is a subgradient, because of the fact that subgradients always lower bound the function. So again, it's a discrepancy between gradients and subgradients. For a differentiable non-convex function, let's just draw this. If I have this function, for example, okay, this is non-convex. If I ask you for a subgradient here, you're going to have a hard time finding one for me. Because if I look at its gradient, it doesn't lower bound the function everywhere, right? So in fact, it has no subgradients there. So I'm actually using subgradients here, which always guarantee that it's a minimum. So for non-convex differentiable functions, the gradient is not necessarily a subgradient. That's why I've tried to put convexity as up in our assumptions. Okay, we're playing stump the professor here. I've had a rough time with these Kkt conditions, but we've arrived at a nice result, which is that they're necessary and sufficient for optimality. A bit of interesting history. A lot of people who are in the older generation will know these as the Kт conditions. Like if you read the Rockefeller book as one of our references, it calls these the Kт conditions. That's because Kuhn and Tucker first published these conditions in 1951. But it was much later. I think it wasn't until the 80s, although I'm not sure. Do you know when? It was well after the Rockefeller book, which was 1970, that people found that this mathematician named Karouche actually had them in his master's thesis, but decided not to publish them. And that was in 1939. So that's why we put the K at the front for his name, because he had it first, so it's Kkt. So if you talk to someone, they might call it the Kт conditions if they're old enough. Many people, including myself and probably Jeff, we use the term Kkt conditions for unconstrained problems. So we use the Kkt conditions basically just to mean that. There's no constraints then on the primal, then none of these are here, right? So sometimes you might call it the subgradient equations or the Kkt conditions, but just don't be confused in the literature. If you see somebody write down something like this, the 0 subgradient condition, and call it Kkt, because it's just a special case of the Kkt. Another interesting thing to point out is that we derive these from the point of view of duality, right? We use the duality gap and some other arguments to the Kkt conditions. But as shown in that Rockefeller book, you can do all of this from subgradients. Right? So I can start with a convex problem by writing it in terms of indicator functions. So I have the indicator that each hi is less than or equal to 0 and each lj is equal to 0. And then I can take the 0 subgradient condition for that convex function, and it looks like this, right? Because the subgradients of indicator functions is the normal cone. That's something we talked about when we learned subgradients. We can actually derive the Kkt conditions entirely from this point of view. So if we didn't learn duality, we could still get them. It just would have been a lot harder. So if you're feeling brave, you can go try to read Rockefeller where he does this. How much time do we have? Okay, let's take a break and we'll come back in a couple minutes. Okay, let's get back at it. We have some examples to go through, and then I want to get to, I hope we have enough time to get through this more detailed example of the KKT conditions at use. So we're going to start off with a pretty easy problem, a quadratic with equality constraints. Okay, x transpose x transpose qx plus cx. Going to minimize that, subject to an equality constraint. So an example of when we do this is if we take a Newton step. Right? We learn Newton's method. If we had equality constraints, then what we've done is we've approximated essentially the criterion by a quadratic, where this q is the Hessian and the c is like the gradient. Okay, and x is going to be our delta. It's what direction we're moving in. And if we had the previous iterate satisfying, say, x equals b, or maybe I should use the iterates to be some, yeah, I'll say a times xk is equal to b. And now I want to figure out what xk plus 1 should be, which is going to be equal to xk plus x, my direction. Then I would choose x to minimize this. Right? I want to make sure that xk plus 1 still satisfies this linear equality constraint, so that means that ax has to be 0 if this satisfies the constraint. And minimizing this is like I'm going to do a quadratic approximation to the objective, where that's the Hessian and that's the gradient. Okay, so an example of where this problem comes up is Newton's method with equality constraints. We solve this at every iteration. Okay. Thank you. It's going to make the math easier. So what are the KKT conditions? Let's just go ahead and write them down. The first one is stationarity. Right? For x, and in this case we only have one set of variables, and I'm going to call them u. And those correspond to the equality constraints because there's no inequality constraints. For x and u, satisfy the KKT conditions, we need to have the following. The first is stationarity. It's convex, so I can write down the stationarity condition as just the gradients, right? Subgradient is just the gradient for a convex function. What's the gradient of the first one? It's the gradient of 1/2 x transpose qx, so that's just going to be equal to q times x. And what's the gradient of the second term? C transpose x, it's just c. Okay, so that's the gradient of the objective. And then I also had, the Lagrangian had u transpose ax minus 0. Right, so when I take the gradient of that with respect to x as part of the stationarity condition, I get just a transpose u. So that's the stationarity condition. Okay, we're all clear on that? Complementary slackness is nothing here, right, because of the fact that there's no inequality constraints. Primal feasibility tells us that ax has to be equal to 0. And dual feasibility, there's nothing because I didn't have an equality constraint, so there's no sign constraints on my dual variables. Okay, so if I summarize these conditions, I can summarize them like this. This times x and u equals minus c and 0. All right, the first one gives me stationarity, the second one gives me primal feasibility. So that's what Jeff wrote down for the Newton step, but he did it from an intuitive point of view. We're just checking out the KKT conditions gives us the same idea. So at each step for Newton's method, we'd solve this system of linear equations, and we take a step in the direction of x. That tells us the direction. I'm going to have to skip this one. This is a non-statistics and machine learning example. I thought it'd be nice to kind of go outside that realm because of the fact that we talk so much about statistics and machine learning. But it's a longer example. It's a little more difficult. In some ways, it's a little more difficult. It's also in your book. So read these slides, and if you want another reference, you can look at page 245 of your textbook. So here's a problem where the KKT conditions are fairly straightforward, and we're going to be using them at the end of this lecture and also next few lectures, so let's go ahead and derive it. Right, we've looked at this problem quite a few times in different ways. Let's suppose this is our problem, the Lasso problem, where we have linear regression, but we want to have sparsity in our estimated coefficients. So what are the Kkt conditions? Well, again, let's look at the stationarity condition. There are no constraints here, so that just tells me that if I take subgradients of this, it has to be equal to 0. And that ends up being A transpose y minus ax. Actually, there's a minus sign there. Plus lambda times s equals 0, where s is a subgradient of the one norm at x. So this is an example in which I called something the Kkt conditions when it was really just using that subgradient equation, right? I have no constraints, so there's nothing for complementary slackness or any of the other conditions. Okay, so let's just rewrite this for a second. This tells us that A transpose y minus ax equals lambda s. And what are the subgradients of the one norm at x? We can write those explicitly. We know what those are. It's going to be either equal to minus 1, 1, or any element between minus 1 and 1 if xi is negative, positive, or 0. Okay, so what does that tell us? In particular, we can just read directly off of this, right? If I happen to have the Lasso fit, so if I knew what ax was, and I looked at the inner product of the ith variable in that design matrix with the residual, if that was less than lambda in absolute value, then this implies that xi must be 0. Right? Because in that case, it tells us from the Kkt conditions that the subgradient was between minus 1 and 1 strictly, and the only time that can happen if we look at the possible subgradients are if xi was 0. Okay, if this is equal to lambda in absolute value, we don't know that it's non-zero. Right? Because I could have had that means I have a subgradient equal to 1, say. It could have been that the variable was positive, or it was 0, and I just chose to have a subgradient equal to 1. But we do know that this direction of the implication. And we can think about this in terms of correlation, if the variables are standardized. If the correlation of the ith variable with residual is smaller than lambda, strictly, then that variable is 0. Okay, so that's going to be something we revisit shortly. Here's another kind of non-trivial fact that you could say from that. Suppose you ran a Lasso problem where you had a bunch of predictors and you just found the solution and you looked at all the variables that had correlation less than lambda and equal to lambda. Then you started adding variables to the Lasso problem that, given this Lasso residual, so I'm going to think of some new variables, I'll call them z, that satisfy this. I just picked twice as many variables z that satisfied that. Then you know, without even solving the Lasso problem, that at the solution with this expanded design matrix where I had a and z as my new design matrix, that all the variables in z are going to be 0. Right? So you don't have to even do the second problem. You had the fit for the first problem, and it just so happened that this was less than lambda, then you're free. You actually have the solution to the second problem. And in a couple lectures, we're going to see this argument can kind of be tweaked in a little more formal way to actually rule out predictors from the Lasso problem a priori without even solving the problem. Some of them. We can say that at the solution, if I were to go to the trouble of solving it, it will have a coefficient of 0. Here's another example. This one is a nice example of how we can confirm some kind of intuitive behavior we expect to have in the solution by looking at the Kkt conditions. So I'm also in the regression setup, but now I have my design matrix is split up into a bunch of groups. Instead of just picking, so I can also split my coefficient vector up into the same groups, right? And instead of just picking individual elements of x to be 0, I actually want to zero out groups of variables altogether. So each of these groups could correspond to something that's scientifically meaningful. And I maybe want to select groups rather than individual components. Okay, well, one of the ways that people do that in the literature is they look at this something called the group lasso problem. And it's very similar to the lasso, except for I replace the one norm penalty by a sum of two norm penalties. And it's very important that this is actually the two norm and not the squared two norm. That's why I'm making sure we know it's a two norm, just putting that subscript there. And we usually have a term here that that accounts for different group sizes, the square root of pi, where p is the number of variables in the ith group. Thank you. Yeah, the slide's missing an x. So I'm actually penalizing just each component of x as its own vector, and I'm taking the two norm. So the thought is that by doing this, we're going to actually choose some groups to be 0 entirely. We'd force some coefficients to be all 0. And for the groups that we choose to be non-zero, we're going to allow all of its components to be non-zero. That's a pretty heuristic, I mean, I can give you a heuristic argument for why that's true by looking at this picture. This is from the paper which was proposed. It's basically because we take the one norm ball and we're going to smooth it out in some direction. If we look at contours now with x1 squared and x2 squared, so that we're going to hit a kink of this sublevel set that corresponds to groups being zeroed out. But how do we know that's actually true in terms of the solution of the optimization problem? For that, we can look at the Kkt conditions, and it'll confirm this, this heuristic idea we have. So let's go ahead and do that. What are the Kkt conditions? I'm going to look at the stationarity condition with respect to each block of variables xi. And that's all there is because there's no constraints. So just like before, I have instead of A outside here, if I'm taking the derivative with respect to the block of variables in xi, I get AI transpose out there, and it's equal to these constants, which just multiply the penalty times the subgradient of the penalty over just the variables in the xi block. Well, remember the penalty was just this, right? So if I take the subgradient over the xi block, I just take the subgradient of this because it doesn't appear anywhere else in the sum, and that's just a subgradient of the two norm of x. So I'll call that Si, where Si is a subgradient of the two norm of x over that block of coordinates. Okay, so what is that? We can write that explicitly from what we know about subgradients. That's either equal to xi over its norm, if xi is non-zero. So it's just the gradient in that case. Otherwise, it's anything in the unit ball, the unit L2 ball. Okay, so these comprise the Kkt conditions here. And just like we did for the lasso, we can now look at this and read off directly and say that, well, if I happened to look at, say, the norm of the ith block of variables transpose the residual, and that 2 norm was strictly smaller than lambda times the square root of pi, then I know that xi must be 0. Right, because in that case, it tells me from the Kkt conditions that the subgradient had a 2 norm strictly smaller than 1, and that can only occur in this case. So if this is true, then all the variables in that block are 0. Okay, if it's not true, in the other case, if I actually get equality here, then I end up, this is the other case, right? This is actually equal to lambda times the square root of pi times xi over its norm. That's the other case. In this case, I can solve for xi. I can just rearrange terms and solve for xi. And it tells me that xi is equal to ai transpose ai plus lambda root pi over its norm times identity matrix inverse ai transpose the partial residual. So the residual when I fit every block of variables except xi, and that's defined on the slide up there. Okay, so it tells us that either, there's two cases, either the entire block of coefficients is 0 or it's equal to this, right? And this is going to be non-zero in every coordinate unless there are some degeneracies and ai times the residual. So it confirms our heuristic interpretation that either group is non-zero or it's 0. This even, if you look at it, actually suggests an algorithm for fitting the group lasso. Right? What could I do? Well, at the previous iteration, if I had some xi, I could look if this condition held. If it held, I'd zero out the group. If it didn't hold, I'd actually take the next update for xi to be equal to this. And I just would repeat that over and over again. And that's actually the first algorithm that was proposed for the group lasso. And it works pretty well. This came down from looking at the Kkt conditions and going right from there. Questions?
How do you solve that for xi, given that xi appears on both sides?
So yeah, the question was how do I solve this for xi, given that it appears on both sides? I was actually not saying that this algorithm converges. I just was saying that you could attack it in an iterative sense. I could start with a guess.
Oh, I see. So you use the previous.
The previous iterate is the one that I actually plug in here. To prove that it converges is a little harder. And the preferred method for solving group lasso now is not this anymore. There are a lot of other methods, but back when this was proposed, it was it was an algorithm. It converged, and people used it, and it just came from looking at the Kkt conditions. Okay, so here's something I always confuse myself about, and I always come back to this same question over and over again, and I thought it'd be helpful to write down on the slide so that I can now permanently unconfuse myself, and maybe you can learn from it as well. So all the time in statistics and machine learning, we look at a problem that's in constrained form, right? We write it like this, suppose, and we say, well, that's equivalent to Lagrange form. I can just put a lambda up here, and for some lambda, these will be the same. And if I have any version of this, for some t, these will be the same. So we call those constrained and Lagrange forms. And virtually every paper you see that has a problem written in it will have this statement. So the question is that true, and how do we know? And I'm assuming here that f and h are convex. So let's think about that. Let's go from constrained form to Lagrange form. So if this problem is strictly feasible, right, then we know that strong duality holds because of the fact that it's convex. That means that there exists some lambda that's greater than or equal to 0, which in this case is the dual solution, such that any solution x star in C minimizes this. Right? Why is that? That's just the fact that it minimizes the Lagrangian. Okay, so the Lagrangian here is f of x plus lambda f of x minus t. And we know that, for example, under strong duality, or we can also just cite the stationarity condition of the Kkt conditions, that if lambda is dual optimal, then x, our prime optimal solution, is going to minimize this. Okay, but that's equivalent to minimizing this problem as long as t wasn't infinite. Thanks. Okay, so what have we said? We said that if it's convex, strictly feasible, then there's going to exist a lambda for which constrained problem is the Lagrangian problem. Okay, let's think about the other side. If we go from L to C, so I have a solution to this problem, minimize f of x plus lambda times h of x. Let's call it x star. Let's think about taking t equal to h of x star. Okay, then let's now go through the Kkt conditions for this problem. Minimize f of x subject to h of x less than or equal to t. Well, the stationarity condition is satisfied because of the fact that I chose x to minimize this. It's the same argument, right? Minimizing f of x plus lambda h of x minus t is the same thing as minimizing f of x plus lambda h of x. So the stationarity condition is satisfied. How about complementary slackness? That tells us that lambda times h of x, I should probably be using stars here, h of x star minus t is 0. Well, that's true because I defined t to be equal to h of x star. That was the proposed bound for my bound problem. And primal and dual feasibility, primal feasibility clearly holds because of the fact that I defined t to be like this, and dual feasibility we have no inequality constraints. So I satisfy the Kkt conditions, and therefore x star is also a solution of this problem. Okay, so let's summarize in this. It's written on the slide here. All the solutions of L as I vary lambda, each one of those is going to be a solution of C for some t. So I think of this as the solution path. Then the solution path over lambda is contained in the solution path over t. How about the other way around? If I take the solution path over t and I only look at the t that are strictly feasible, then each of those is a solution of lambda. But if it's not strictly feasible, then we actually don't know that it is a solution for some lambda. So it's almost an equivalence. It's almost always an equivalence. But strictly speaking, it's not equivalent. Okay, so that's maybe a minor point, but a point to keep in mind. What saves us is that in almost all of the cases that we deal with in statistics and machine learning, the only points for which it's not strictly feasible are when t is 0. Okay, so if t is 0 and it's not strictly feasible, then I can actually achieve a solution in the Lagrangian form by taking lambda equal to infinity, right? Because I can think about as I take lambda equals infinity, then I'm basically enforcing the constraint h of x equals t, right? And if t is equal to 0, then I'm enforcing the constraint h is equal to 0, and that's the only time that those two problems are equivalent. So if t is 0, if the only value of t that leads to a feasible but not strictly feasible point is 0, then we get equivalence. So for example, whenever h is a norm or a semi-norm in all of the problems that or I shouldn't say semi-norm, whenever h is a norm in all of the problems that we study in statistics and machine learning, that's usually the case, then we do get perfect equivalence. Otherwise, there's this minor non-equivalence. But you can just remember this picture and refer to it in the future. Okay, how much time do I have left?
7.
Okay, that should be enough time. So here's a more in-depth example of the Kkt conditions, and it's a pretty simple set of arguments. They're not terribly complicated, but it leads to, I think, a somewhat surprising result. And it also gives us a very definite answer of why we get sparsity in all of the problems with one norm penalties. So here's the statement. I'm just going to go ahead and say it. If f is differentiable and strictly convex, so take any loss function you want as long as it satisfies those two criteria. A is a design matrix, so again we measure our variables on the columns and our observations on the rows. And lambda is any positive tuning parameter. Then if we look at this problem, minimize f of ax plus lambda times the L1 norm of x, then in general this might not have a unique solution, right? For example, if A has many more columns than rows, then this whole criterion is not strictly convex. Even though f is strictly convex, this whole criterion is not strictly convex in X. So let's just think about the Lasso problem to be concrete. Right, if I take A to have 1,000 columns and 100 rows, I don't know that the solution is going to be unique. But if the entries of my design matrix A are drawn from a continuous probability distribution on the set of all matrices in R and P, then with probability 1, the solution is unique and has at most the minimum of n and p components. So what's the statement is that x star is unique, and the number of non-zeros in x star is less than or equal to min np. So for example, in our thought experiment, if p was 1,000 and n was 100, when I solve this problem, as long as my predictor variables are continuous, then with probability 1, I'll have a unique solution, and it'll have at most 100 non-zero components, even if there are 1,000 variables. Okay, so here's a more definitive statement as to why we get sparsity in all of these problems. So the only time we can have a non-unique solution that has more than this number of non-zero components is if we had, say, discrete predictors, or we had predictors that were mixed continuous and discrete. If we have continuous predictors, then that never happens with probability 1. So we're going to prove that, hopefully. And yeah.
Is that statement dependent on the value of lambda?
Very good question. The question was, is this independent of the value of lambda? And yeah, it is. So I can say that the entire solution path is unique with probability 1, and every element on the path has a most minimum NP components. So if I want to, I could rephrase this to make it even stronger. So this is true for all lambda with probability 1. So let's do this quickly in the amount of time we have left. The Kkt conditions look like this. Right? What are the subgradients of my criterion? Well, since this is convex and differentiable, I just take its gradient. From the chain rule, it gives me this. Actually, there's no minus sign here, sorry. Plus lambda s equals 0, where s is a subgradient of the 1 norm, just like we had for the lasso. It's the same idea. And now I'm going to put this on the other side and just look at it like this. Right, and s is the subgradient of the 1 norm, which means that it's either equal to the sine of xi if xi is non-zero, and if it's equal to 0, it's anything in minus 1, 1. So the first thing to note is that that ax is unique. Okay, I'll maybe leave you to think about why that would be true. Even though x can't be necessarily unique, ax is always unique, and it basically comes from the fact that this here is strictly convex in ax. So I can never have ax being non-unique. And that means that s is unique from this equation, right? Because s is uniquely defined in terms of ax. So we're going to go ahead and define this set to be the set of all j such that the jth variable has inner product with the gradient equal to lambda. So anything outside of s we know must have a 0 solution, must have a 0 component at the solution. Right? We know xi must be equal to 0 for all I not in s. That just comes from the Kkt conditions. Right? If that was strictly less than 1, then it has to be 0 by our definition of subgradients. So let's go ahead and first assume that the variables, if I only look at the variables that have this equal correlation of equal inner product to lambda, let's assume that they were not linearly independent. So their rank was strictly smaller than s. Then that's going to mean that I can take one of them and write it as a linear combination of the rest. So I in s, or j in s, j not equal to I. Okay, and now I can take an inner product on both sides with the negative gradient, and I get that si times lambda equals the sum of cj, sj times lambda. right? Because from the KKT conditions, every variable satisfies this. I'm going to take the inner product with the gradient. Okay, I'm going to multiply now by SI and divide by lambda, and I just get that this is true. Okay, and I'm going to call these constants AI, or AJ, sorry. Okay, so what have I shown? I've shown that actually SI times AI is equal to the sum of AJ times SJ AJ, where AJ satisfy this. So what does that mean? It means that actually SI times AI, that variable, it's in the affine hull of the rest. So when I take affine spans, I have to take all linear combinations such that the coefficients add up to 1. That's exactly what this is. So I've just concluded that if that set S was not linearly independent, then I have AI SI is in the affine hull of A SI SJ AJ for J in S minus I. Okay, so I'm not going to show this because we're really running out of time, but a very simple probability argument tells you that if A has entries that have a density over R and P, then this can't happen with probability 1. So you can just look at the picture to think about it. Suppose I have 3 variables here. Okay, they determine an affine space of dimension 2. If I look at any other variable and it has a continuous density, or has a density on R3, then it's going to lie in this plane of dimension 2 with probability 0. Right? Even, no matter what the correlation between A and these variables are, as long as there's a density, it's going to lie in that plane with probability 0. So if A has entries drawn from a continuous probability distribution, then what we've just shown, this can't happen with probability 1, which means that with probability 1, the rank of these variables is equal to the size and the number of variables. So in other words, those variables are linearly independent. And if that's true, then this has to be equal to the minimum of n and p, because this matrix has number of columns equal to p and number of rows equal to n, or has number of columns equal to s, which is less than or equal to p, number of rows equal to n. So it can't have rank exceeding its dimensions. Okay, and the very last step in our argument is that we say that, okay, so that's linearly independent. So let's go back to our optimization problem, and now let's just plug in 0 for all the variables outside of S. Then that gives us this as our optimization problem, right? We've partially solved. So now the goal is, because we know it's 0 outside of S, to solve for the variables inside S. But because A is linearly independent, or A has full column rank, the columns of A are linearly independent, this problem is strictly convex. Right? Its Hessian is A S transpose the gradient of the Hessian of AS XS AS. Okay, we can think about it in several ways, but this problem is strictly convex. And therefore it has a unique solution. Okay, so we just proved that the solution is unique and has support at most this large with probability 1. I think we're out of time. Maybe I should take questions just after the lecture. See you guys on Tuesday. Thanks for sticking to the end.